So good morning, and so I'm going to talk about some practical things that I hope will give you some insights into your work, help you with completing your crystal structures, getting them finished, published, and so on. And I realize that people from different groups are probably doing it different ways, so I'm going to try and keep it very general. Anyway, let's go on and I'll explain my strategy here. So Sankar suggested that I teach the structures solution part with WinGX, but actually I'm not going to do that. But maybe later, if you want that instruction, he'll come in and give a short presentation on WinGX. The thing is that there's so many different interfaces for doing this, so I don't want to really focus on any one. Because some people will try SHELX, some people will try OLX2, some people will try nothing. So what I'm going to show you is the nothing approach, which is to just use the DOS prompt, the command prompt. And that's the way I learned crystallography. And inside all of these programs is basically the same thing. It's just the interface is just telling you which button to press to get where. But what it's doing, it doesn't really differ because everyone's using the SHELX software with very few changes, and that's what I'm using too. It's the SHELX approach. Now, George Sheldrick was writing this software in the days of Fortran, so in some ways you might find it a little primitive, but actually I think he's a brilliant man, and I think what he's done for the community is just incredible. Because before he came around, there were different programs from different institutions, you know, Caltech, Brookhaven, you name it. And each one was a separate program. And of course, in those days, we were using IBM cards. So it was really a relief to have somebody come along and put all of this together. And as time has passed, he's kept on changing his programs and making them more and more modern and more efficient and faster. So anyway, we will see. So let's go to turn this on. Always helps to turn it on. Okay, so some good data practice. Again, I keep emphasizing this. If at all possible, do use a low temperature data collection. I have probably only observed decomposition in the X-ray beam once or twice in my career of collecting thousands of crystal structures, because I always have used low temperature. And in part that's because Professor Håkan Hope, who was at UC Davis when I arrived, was one of the early users of low temperature, and he also really emphasized it and had everything working beautifully. It took the instrument manufacturers many years before they got it all working as well as he did. Icing was one of the big problems, but it isn't a problem if you know what you're doing. Okay, so why do you do it? Because you eliminate decomposition. The only thing I've seen decompose really badly was a silver compound, because it's so light sensitive and the X-rays are pretty bright. And you can have decomposition of your compound, even at low temperature, if the light is too strong with silver compounds. Of course, in protein crystallography, you really have to use a cryostat to get good data, and that wasn't realized until pretty late either. What people used to do if they were doing proteins is they would have to collect data for a while and then swap crystals to finish the data collection, and then figure out how to merge the data. And it was very complicated until they finally realized they just needed a cooling stream. Okay, so the results are going to be better. You're going to get more data. Thermal motion cuts off the high angle scattering so that you get less data, and that, of course, affects your precision. I want to show you an example using helium just for fun. I've only tried it a few times, and it's hard to justify the expense. Actually, helium is very expensive. I believe at the time I was doing it, it was about $600 for maybe a day and a half, and then it was gone. And it's much more now, in fact, because the helium supply has been, you know, it's a natural product. It comes from radioactive decay. You can't make helium, so you have to collect it. And so it comes from certain wells, and once the radioactivity has kind of gone through a cycle of half-lives, then you have less helium, and it gets more and more expensive. Anyhow, so if you use helium, you do get inner atomic distances approaching those of neutron diffraction. I already mentioned that. I want to show you an example. Okay, so this was the 90K structure was published a long time ago, in 2004. You may recognize some of these names. It was a really cool compound, very nice, and there wasn't really no problem with it, but I wanted to try something that had nice crystals, and so I did it at higher temperature and lower temperature. And I hope you can see, these are all plotted with 50% probability thermal ellipsoids, which is the typical choice. The things that are most likely to really move, of course, are things which have librational motion. So like a perchlorate really is tending to go like this as you raise the temperature. And you see that in the thermal ellipsoids because they're elongated and they're also kind of, they look like they're rotating. Just their shape, right? They're elongated and perpendicular to the bonds. Then there was a acetonitrile, a couple of acetonitriles in the structure. And then the middle atom here, which was manganese. Things also tended to librate around the manganese because it's the heavier element. So you do see some larger motion at 170K. It looks, I mean, it was a nice structure at 90K. But what's really interesting is how small those thermal ellipsoids are at 10K. I mean, it's so small that in some cases the refinement software thought there was a problem because they're much smaller than you're used to. So how small? Let's look at that. So here I'm just listing the equivalent thermal parameter called UEQ. And that's always listed also in your LST file when you're doing refinement. Because if you're doing anisotropic, it's a tensor quantity. There's 6 parameters. And actually, to get UEQ, the way it's calculated is a diagonalization of that matrix. But it's very close to being just the sum of U11, U22, U33. In other words, the 3 directions divided by 3. So it's very close to being just the average of the diagonal elements in that matrix. The off-diagonal terms are small, that's why. Anyway, so UEQ values I'm reporting for the 3 temperatures, and this is just the perchlorate. And you see how they really get really small, less than 0.01. And the oxygens are also affected. And here I've just averaged the oxygen values, which are actually changing percentage-wise the most, because you're cutting down on that librational motion. With me on that? See it? Okay. So, missing a slide. There was another slide. I don't know, maybe it'll come back. Okay, so these are some more pointers about, darn it, where is that slide? It's annoying. Maybe it got out. No, looks like it's not there. Okay. I wanted to show you the distances as well, but somehow it got omitted. Sorry. So here's some more strategies for data collection. The IUCR requirement is that the resolution is 0.83 angstroms or better, and that corresponds to 50.5 degrees in theta if you're using molybdenum radiation. It's a higher angle if it's copper radiation. There's a way to see if you're going to get that resolution before you even start collecting data, just by looking at the spots and measuring their intensities on the screen. So what you can do is collect for a longer time sometimes to bring those high angle reflections within that range. And if you have a really difficult structure with a lot of atoms, you might find that you really should be collecting to even a better resolution. 0.65 would be achievable if you have a heavy atom present, so don't just cut it off because I said 0.83. Cut it off higher, a better resolution, and you'll have more data and you'll be happier. Otherwise, you're just throwing away good data if you don't do that. I already mentioned last week about absorption effects, so you have to take that into consideration too. If you have a heavy absorber and you're going to be using even molybdenum radiation, don't use too big of a crystal. Keep it small. A half of a millimeter crystal might just actually block the X-ray beam. Now with area detectors, it's quite easy to get fourfold redundancy, and this is part of the strategy of collecting the data. It depends a lot on the instrument, so I won't go into that too much, but if you possibly can get fourfold redundancy. The only time really that's an issue is if it's triclinic, because with triclinic, you really need half of the reflecting sphere. Do you understand what I'm saying, reflecting sphere? Not really, okay. So we have HKLs that can be positive, they can be negative, they can be partly positive, partly negative. If you think of all of the permutations of that, there's 8 of them. So you can think of there as being octants in a sphere containing HKLs that are positive, negative, all negative, and so on. And then as 2 theta increases, you're going to start diminishing the available data because it's weaker and weaker and weaker as you increase 2 theta. So you can think of it just basically as a sphere, okay? And if we need half the data, then we need half the sphere. If we have monoclinic, we only need a quarter of the sphere. If we have orthorhombic, we need an eighth of the sphere. If we have cubic, only 1/48th of the sphere, and so on. So if you can get the redundancy, especially since you don't always know if your space group's chiral or not, a chiral space group is going to need more. So just to be safe, you might as well go for fourfold redundancy. Any questions on that? Okay. So if you can, sometimes you can access the diffractometer either in the lab where it's being collected or by TeamViewer or some other program that connects to the diffractometer. You don't have to wait for it to finish. You can start reducing the data, trying to solve the structure, and after you have maybe 100 frames or something like that, you can usually get the structure. So why waste a lot of time? You know, somebody else might want to use the instrument. And maybe it's nothing like what you expected. Like S8, sulfur, it is often a product. It makes beautiful crystals, and I don't know how many times we found sulfur to be the crystal that we're looking at and not the desired material. So make sure it's what you want. A double check is to use one of the databases, like the Cambridge Structural Database, which I believe is accessible here. Is that right? You have access to that online as a client? Yeah? So you can check easily? Yeah, it's very, very valuable. And polymorphs are lots of fun. It's interesting to see if there is a polymorph. And many times you get a structure and you think, okay, that's it. I'm happy, I'm done. But if you go back and look at the slide, you might see a different habit. You know, there's plates as well as needles, or there's a different color. So, you know, maybe it's a minor product, but it's still interesting to see what else might be there. It might tell you something about your synthesis even. So don't overlook what's on the slide. Okay. So I'm going to show you an example here where there's a lot of things here that are important. If you've chosen the correct unit cell and crystal system, and then you're doing data reduction, you should see upwards of 100% correlation between where the spot is found and where it's expected to be found. So that's part of the data reduction process. Now the unit cell and crystal system is determined very early on. It's determined before you know the space group. That's sort of the first step. So it's possible that you won't even have the correct space group at that point or the correct crystal system until you've solved it. So you might need to go back and do this again. Twinning is an issue which we haven't discussed much of. One of the ways to handle twinning, though, if you do have it, and you can't avoid it, is to do a twin integration. In that case, you would have 2 overlapping unit cells, and you're actually reducing the data simultaneously with both of them, and then later on you separate it. This is really only successful if the 2 unit cells are well separated, though. If there's a lot of overlap, it becomes very difficult, and I think I prefer some of the other methods for handling twins. Later we'll talk about that. Anyway, whatever you use kind of depends on your instrument. Roughly what you're going to get, though, after the data reduction step is probably a raw file. I think most of the instrument manufacturers use that. So this contains not only the HKLs, so it has, on each line it will have HKL, so integers, and then an intensity, which I guess we used to be counts per second, but it's just intensity. And then following that is the sigma for the intensity. And then there's a bunch more numbers that you probably won't worry about, but they're direction cosines that relate your crystallographic axes to the instrument axes. The importance of the direction cosines is when you're doing an absorption correction that's called an analytical absorption correction, because you need to know how the crystal faces and the beam direction are related to the instrument directions, so that you know what path the X-rays must have taken through the crystal to do this analytical absorption correction. I only really do the analytical one if I have a lot of heavy atoms, but then it can be dramatic, the effect. And in order to do this, you need to have an instrument that has a camera attached, like a video camera. I don't know, does yours have that here at Kanpur? You have the videos? Okay, good. Yeah, so some people recommend that you always do the video, just in case you want to go back later. If you have the videos taken and you've stored it on your hard drive, you can still go back even if the crystal is no longer on the instrument and index the faces, as long as you have that video. So it's optional. It doesn't take more than a minute or two to do it. Okay, so the other way to measure the crystal, you can measure the crystal with the video, or you can do it under the microscope. I always ask the students to be there when the data collection is finished and do the integration there or else remotely, and make sure that it actually finished and there was no interruption in it. Because once you've taken the crystal off, you may not be able to put it back on. It might decompose. So make sure it really did finish the data collection, and that it didn't grow a big ball of ice around the crystal, which sometimes happens. And if there's a big ball of ice, then that's going to really mess up your experiment, because it's blocking the X-rays. It's making big powder rings of ice on the images, and it's not really nice. Sometimes there's a power outage and it stops for a while, or the detector has a fault or something. So I really recommend that you make sure it's finished before you take the crystal off, if possible. Okay, and measure the crystal dimensions. Don't forget to do that, because you need to enter that at some point. And also note, either in a document on your computer or in your lab notebook, the color and the habit. The habit being the form, what we call the crystal form. And some of the terms people use are prism, needle, plate, block, parallelepiped. You can actually call it whatever you want. I think it's acceptable now by the SIF people. But these are sort of the common things that you would say about the habit. Okay? So, like colorless prism would be okay. Whatever you think it is. But do put something down. Don't imagine that you'll remember it a year later when you go to publish this. Just, what was that exactly? Put it in your notebook. There's that bird again. All right. So these are all just kind of good practice clues. Now, I'm most familiar with the Brooker software myself, and it was originally written for computers that had no graphics or anything. They were just lines, and we used MS-DOS. Some of it was even on cards. So these are some of the popular graphical user interfaces. I know that WinGX is popular. Some people have switched to OLX2. A lot of the people that I really like as crystallographers really like SHELX. Has any of you ever tried that? It's all of these are free. SHELX I've played with a little bit. It's very nice, actually. The person who wrote it worked with George Sheldrick for a long time, so he's incorporated the Sheldrick software. But it can do some automatic things for you, like updating the weight as you refine and sort of things like that. Then for structures, basically just structure solutions, SIR 2014. Maybe there's a newer version now, I'm not sure. This student who visited me from Japan used this program called Yadokari. I don't know if you've ever heard of that. But there's many of them. People have written them over the years. Different countries probably have different ones. So to avoid showing any favoritism, I'm just going to use the DOS, the command prompt. They're all using basically the same software underneath. Okay, so to use the command prompt, which was probably before you were born, right? There's a prompt, which is this forward thing, the greater than sign. And that's where your current location is, your directory. It's just going to tell you, like C:" thing is your root directory. It's like there. And then it's not convenient to put everything into the root directory, so you should have a subdirectory for your data. So to go to the subdirectory, you can make the directory with MD, make directory, and then a name. And that's, say, you're like MM01 or something like that. So you have to keep track of your files systematically or you'll get really lost. Then to go to that directory, you would just say CD MM01 or whatever you called it. And if you want to see what files are in there, you just say dir, standing for directory. It's like list. Okay. Now I'm not giving you all of the details of this. There's whole books written on command prompts. If you do decide to use command prompts, you probably want to learn some of the other commands here. But these are the basic ones. If you want to delete a file, just say del and then give the file name. If you want to make a copy, say copy and then name the first file and the name of the file that you want to copy to, name. And if you want to rename a file, just REN for rename, and then file 1, file 2. It won't do it if file 2 name already exists. Okay? So there's probably only, it's much easier than learning another language. You just learn some selected names and you can do everything. Now, this is, I think, really useful to know the file extensions thing that follows the dot. You can see these in all of the GUIs because they'll all be using the same file extensions. Oops, okay. So these were all named by George Sheldrick at some point. So the file extension ABS is the listing file from running the absorption correction program, usually SADABS. So that's a listing file, output file. They all have some kind of mnemonic that makes sense. PRP is the output file from running XPrep. So you want to go back and look at what you did in XPrep. It's a listing file, so it's really quite useful. I am going to make PDFs of these. I have done the ones last week, but I haven't put them on the website. But there will be a website I understand that you can access. So LST is the listing file from almost everything else that you do, like structure solution or structure refinement. So it's an output file. Now, a lot of these will be overwritten, and so if you do want to save what you did before, then figure out some way to save them so they don't get overwritten, or else maybe some of the software you're using doesn't overwrite them. But a lot of times I'll just put in something like SAV for save or something like that in the name, so I remember that it's an older one. Okay, HKL, I think that's your data. That's the important part. That's your structures in the HKL file. Big file, can be very big. But all of these are basically ASCII2 files. You know, you can open them in Notepad. You can open them in simple text. Depends on your computer. But sometimes, like the INS file is also, unfortunately, an extension that used to be used in setting up computers. And so if you want that to be accessible, you have to tell your computer that it belongs to Notepad, that it doesn't belong to instructions. Okay, it's a Notepad file. And also, you usually cannot email an INS file because it's blocked, because it's an instruction file. Somebody could consider it as, a virus. It could be a virus. It is not, but I mean, some people might think it is, so sometimes you can't send them, they're blocked. Okay, FCF stands for structure factors. I'm not exactly sure what the FC part is, but anyway, these are listings of structure factors, probably structure factor calculation file, I think, FCF. Used to be required a lot, but we don't really look at them very much anymore, but it's a big listing of FOBS versus FCalc with different kinds of formats, depending on what you tell it to do. CIF, crystallographic information file. That's the last thing you do when you're solving and refining a structure. Usually it takes several iterations before you're happy with the CIF, but when you go to publish, that's what you send in. And almost all the journals, virtually all the journals, require that now. And then that will be archived in the Cambridge Crystallographic Database. And we'll spend quite a bit of time talking about CIF. I think that's where a lot of people get stuck. And I am constantly helping people with it. And CHK is the validation file, the output file from running a CIF checker. So there are some programs now that will check your CIF for you and then spit out alerts and tell you made a mistake. Okay, so you have to run the CIF checker, open the CHK file, and see what the errors were. Okay, so those are just some of the file extensions, but some of the most important ones. Yes? Any questions? Okay. Okay, now for Brooker, there's certain other ones that I always archive. If I'm finished with a structure, I don't necessarily save the whole data collection files, everything on my computer. I will put them on a hard drive somewhere else because those are really big files, gigabytes. But the ones that you should probably keep together, I would say keep P4P, which is the output from XPrep. And then this one, the underline LS, is and again, it's a listing file from the integration. Each run has a different listing file, but the final one is going to be underline 0M because it's the merged one. Or you could keep them all. I would recommend that you keep that. Those are not terribly big. These files are kind of big, so I usually also archive them somewhere else. I keep the apps file. You need that to finish your CIF, so keep that one. So when you get down to having to write your CIF, you make sure you have all these handy. Don't throw them away. Now, to run the SHELX programs from the command prompt, it's generally just a matter of writing one of these names followed by a file name or maybe a couple of file names. So it's not too horrendous. Let's start with SADAB. So that was the absorption correction program. It's going to ask you for raw files, and that's all, just raw files. Then sometimes you do need to go back and rerun it for one reason or another. So you might keep the raw files handy until you're sure that you're done. Okay, at the beginning, XPrep, really, really nice program, which suggests the space group, gives you statistics, systematic absences. it has actually a whole pile of utilities that most people never even look at, because usually you just go return, 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 and say, oh, okay, now I have my ins file and my HKL file, and I'm ready to go. Okay, well, that works for a while. But the only things you need for running xprep are the unit cell dimensions, so your unit cell, and your HKL file. One way to run it quickly without having to put those in is if you have the same file extension or file name for those two files. So in other words, xprep, you could just say mm01 if I already have these files, P4P and so if those files both exist in the same directory that I run xprep, it will just pull them up and it'll use both of those. But if they have different names, okay with that? You have an option of doing it this way. So in the first file name, you want to put in the name of the HKL file, and in the second one, the name of the P4P file. But you don't need to write the file extension, okay? So if those two files have a different name, you just put in the name, and the program will pick them up. First the HKL, then the P4P. Otherwise, it'll ask you for them. But I find it handy to just do it maybe this way, so I don't have to remember what they were. Before I even run xprep, I see that they are there and that they have the names that I'm expecting. Okay? So I'll show you that. And then the old package of SHELX, there was a package called SHELX TL Plus that had SHELX S as one of the structure solution options, and it embodied both the Patterson or the direct methods method for solving a structure. And to run that, you need an INS file and an HKL file. You could also use raw, but people usually don't. And then it outputs res and LST. It doesn't change HKL. To tell you the truth, hardly anybody uses that anymore because there's this new program called SHELX-T. Have y'all used SHELX-T? It's like magic. It works so well that you almost never need to use direct methods or Patterson methods. Yes, you heard of it? Okay, yeah. So it's only been around for 3 years, XT. And I was one of the beta testers for it. I think it's amazing. I have tested it on structures which I could not solve otherwise, and they just come out immediately. It's extremely powerful because it uses what's called a dual method. So it's actually using both a kind of direct methods and Patterson. And in addition, it's using chemical connectivity knowledge to give you the most reasonable result. So it's extremely sophisticated. It also suggests optional space groups that are similar to the one that you would most expect. For example, P21 over C, it will select that one. It will also select maybe P21, PC, P2. So lower symmetry versions of that same space group will be output. Usually, though, it's the first one that comes out, the underline A, that's the correct one. But sometimes it's the other ones. Rarely, but sometimes. Anyway, I'll give you an example of that. So XL, followed by the file name. XL is the refinement program. And you run that many, many, many times in the course of solving a structure, of course. I should also say that that also has a new version, 2017. If you're using the old version of SHELX-L or XL, don't. Okay. One really good reason why you shouldn't is that the old versions like SHELX-L97 don't write a CIF that has the HKL file in it. The new versions will write you a CIF that has all of the data in it, the HKL, and that's what we need to archive nowadays. That's required by the journals, that you archive the data. So use SHELX-L 2017/1. You can get it from the SHELX homepage. It's free. There's a 64-bit version and a 32-bit version, and you can just download it and you can install it on your computer. And you may have to sign up as a user, but there's no big deal involved. It doesn't cost anything. He just wants to know the names of all the thousands of people that use his software, and then you can download it. So go to the SHELX homepage, and there's also manuals and other frequently asked questions there. There's a lot of good stuff. Okay, now, molecular geometry is, of course, is necessary for solving a structure. You need to look and see if what you're doing is chemically reasonable. So I like to use XP, which was also written by Sheldrick. Unfortunately, this isn't on his homepage because it was put out by Brooker, but it actually is being used like in OLX2 and WinGX. So I don't know if you really have to worry about copyright anymore of XP because everybody uses it, or some version of it. I will be using it from the command prompt. I'm just so used to it, and most of the old crystallographers like me use it. So I can tell you that. Why would you use anything else? It does everything you want. It's great. And it can also output graphics for publication. So we'll be talking about those programs by and by. Let's go on here. Okay, so XPrep. We talked about this a little bit already. It's going to help you figure out the space group. You can get estimates of how many atoms are in the unit cell, how many are in the asymmetric unit, what's the highest resolution that you have, and what final agreement factors you can expect, what your R value might be. And if you run XPrep and some of this information looks bad, you might just say, maybe I need a better crystal. Maybe I should just stop here. Because if you have poor resolution, you're just going to struggle, really. Get a better crystal. Okay, so then you continue to set up the files. And this is what a P4P file looks like. Now, this again comes from Brooker instrumentation. This is an old one from a smart diffractometer, which we don't even have anymore. But it has similar information all the way through. So this is, again, a diffractometer file, but you'll get it. It has the unit cell here. So A, B, C, alpha, beta, gamma, volume. Cell standard deviations, blah, 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 blah. Now, standard deviations, maybe I'll just mention that now. The thing that you put in parentheses there at the end of pretty much anything it should range between 2 and 19. That's the range of values that are allowed to go in that parentheses. So sometimes the software, like here you would write 9.0635 parentheses 4, because the 4 is in the last place there, and that's fine. But what if it said 9.0635, and then it said it was 0.0041? How should you write that? Okay, that's unrealistic to have such a big number like that. And you want it to be a number between 2 and 19. So I would probably round this up and make that a 4 and cut that out and then rewrite it as 9.064 parentheses 4. See? Because the 41 falls outside this range. Okay. So pay attention to that, and if you do it according to the IUCR recommendations, people will believe you're a real crystallographer and say, wow, man, that's great. But if you report these big numbers all the time, then they're going to say they don't know what they're doing. So, yeah. So some programs will allow you to enter this when you collect the data, but in this case, I did not. So ORT1, ORT2, ORT3, those are those related to those direction cosines I was talking about. So this is a matrix that relates your crystallographic dimensions to the X, Y, and Z coordinates of your diffractometer, whatever you call it. So this is a important matrix for continuing on. It will be used for data reduction. So this is what allows you to predict where those spots are on the frames. Okay, so that's the part of the P4 P. It goes on and on and on, but that's the important part. Now this was a structure that I did also a long time ago, but XPrep hasn't really changed. I want to point out some things here that you may overlook because you're in a big hurry and you just want to get to the ints file. But so here's, again, ABC alpha, beta, gamma. It's telling you how many reflections were read from this file. And the mean I over sigma, 16.56. That's an excellent I over sigma. Look for it to be about 6 or more. If it's less than 6, if it's much less than 6, I think you're in trouble. If it's 6, which is it's this last row here, you'll probably be able to get the structure fine. This one is fantastic, so yeah, that was an easy one. But you see what it gives here, the total number of reflections which would fit an A lattice, a B lattice, a C lattice, and so on. No, these are the exceptions, okay. So this is what you would throw out if you insist that it's an A lattice. It's the opposite of intuition. You don't throw out anything if it's a P lattice because there's no restrictions at all. But if it's a C lattice, you have to throw out all the reflections for H plus K or even. All reflections must be omitted because that's the extinction for a C lattice, and so on and so forth. So in this part, you want to look for the thing that's all zeros because there's nothing to throw away. You don't want to throw away a ton of your data. That's throwing away half the data, right? And then the mean I over sigma for those that would be thrown away, and the mean intensities. So you would be throwing away really good data if you selected any of these special lattices. So this is a P lattice. The Niggli cell is pretty much not used that much anymore, but if you did want to compare this structure with another structure, that might be useful because they could be in different settings. It could be in some way a different setting, like P21 over C and P21 over N are two different settings of the same thing. It's just how you define that glide. So C glide goes along C, and N glide goes along the diagonal. But it's basically the same, just a different beta angle. Okay, then it's going to search for higher metric symmetry. In this case, it only found one possibility, so option A, and option A was selected. This number right here, R int, is a really close guess of what your final R value will be, actually. So it's how well equivalent reflections agree with one another in their intensities. So I'd like to see an R int that's really small like this. Clearly, this was a very good crystal. Then it goes on to space group determination. Again, it's exceptions. So we already saw these exceptions here with A, B, C, I, and F. Yeah, that's all just a rep. Lattice type P is selected. Now, mean E squared minus 1 helps you distinguish between centrosymmetric and non-centrosymmetric possibilities. This number is smaller. It's telling you that right here what you expect. It's close to 1 if it's centrosymmetric, and it's 0.7-ish if it's non-centrosymmetric. It's called a normalized structure factor. I don't want to go into it, but the program will calculate that for you and help you a lot. Then systematic absence exceptions. Okay, so again, it's sort of backwards. In this case, let's say there's no exceptions here, no exceptions here. For the N glide here, there's only one reflection with intensity greater than 3 sigma. That's 3S, 3 sigma. That would be counted for an N glide. So actually there is an N glide in this structure because all the rest of them that are being thrown away have an intensity of less than 0.5. So that, yes, there is an N glide, and it's along the A slot in the space group name. But the N, remember, itself is a diagonal. But it's because it's in the A slot that tells you how it reflects. There's also a 2-1 screw axis in the same slot there. So which one do you put in? Do you put in the N or you put in the 2-1? Well, it turns out that the N is what is recommended, although 2,1 also exists in the same direction. So that's confusing enough. But if you have access to the international tables, you could see that both of those are listed. Then there is also an A glide, which is a translation along A, but it's in the B slot. So this dash, A dash, is talking about, like in the space group symbol, like here. Okay, and then the 2 sub 1 again is a subset of that, and then a 2 sub 1 along C. Okay, so taking all those things into account, and again, looking at the ones where there's either 0 or a very small number here, that means you're not throwing away anything important. 2 possibilities. One is centrosymmetric, that's B, and the other one is non-centrosymmetric, that's A. Both of those are in agreement with all of these absences or extinctions. So which one do you pick? You pick the one that has the lower e squared minus 1. Okay. So A, and it says A. Yeah? Now put in the formula. You may not know the exact formula. You can make a wild guess because you're not stuck with this one. Later you can change it. I think I put in pretty close to what it was, and that gives a Z of 4. Now looking back over here, I happen to know, because I really know the space groups really well, that there's 4 general positions in PNA21. So that means that there's no symmetry incorporated into the molecule, and that it has 4 molecules in the unit cell because there's 4 general positions. This is just an organic molecule, so that's reasonable density for an organic molecule. And the non-H atomic volume, 17.2, is also reasonable. So this is a rough guess at the contents of the structure, and it looks good. So this non-H atomic volume should probably not be more than about 25 at the most, and usually it's between 15 and 25. And then this actually gives you the percents. F000 we haven't talked about. That's just the number of electrons in the unit cell. So just count up the number of electrons in that formula, and that's what you get. And it knows it's molybdenum radiation, and this is the linear absorption coefficient, very small, because it's organic. Then it's going to merge your data according to the Laue symmetry and so on. And when it does that, again, it gets nice low values of R int and R sigma. And so then it's merged, and there you go. Okay. Then it sets up the file. So it's always going to set up the file like this, but you don't really need the temperature to continue. I just put that in. Tref would be the direct methods algorithm, which we usually, again, don't use unless you feel like it. But if you use SHELX, it's great. But SHELX reads this file. You don't need to change it. So you do need these certain things. It will not work if you don't have a title followed by up to 76 characters, actually, because, again, this was written in Fortran, and IBM Card has 80 columns. So you can write anything you want after title as long as you don't overdo 80 characters total. All right? Doesn't matter. You can write whatever you want there. I got this crystal from blah, 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 and he thinks it's something, or whatever you want. Unit cell, so the first thing is the radiation wavelength. So for molybdenum, 0.71073 angstroms. Then ABC, alpha, beta, gamma. The standard deviations are underneath. And ZER is the number of molecules in the unit cell. So it's actually Z plus error. It's for ZER. Notice everything's 4 characters. That's always going to be true in these files, that everything in this first column there has 4 characters. That's, again, left over from Fortran. Okay. Then lat, which is the, it's just, this is set by the program. I have another slide which gives that. Then the symmetry operations, but XYZ is always assumed. So in addition to XYZ, there's 3 more general positions, and those are listed there. So you always have to have these things. I think this line could possibly be eliminated in some instances, but you do have to have title, cell, lat, and sem if you want to use the symmetry. In some cases, you want to just remove the symmetry and just assume it's P1. You can do that too. SFAC lists the scattering factors that you need for each of the atoms. Almost always you start with C and then H. And then after that could be alphabetical or heavy to light or whatever you want. Unit is the number of each of those kinds of atoms in the unit cell. Both of these are not written in stone. You can change them as you solve the structure and decide, well, I forgot about the chloroform, so I need to add chlorine to that or something like that. The temperature is in Celsius. Okay, so this was in the neighborhood of 90 Kelvin, around there. Okay, so it's minus 184 Kelvin. So it would be, I guess, about 89 degrees Kelvin. And TREF means direct methods. Then you must have the last two things, HKLF4 and END. HKLF4 is the 4 signifies a particular format for the file, and that's usually what you will use is 4. Okay, so it's ready to go now. It's ready to solve. And this was this structure. I think I maybe showed you this one before. It's diphenylurea. And it popped right out. So some of the things that you might want to look at, though, are the dihedral angle between these two phenyl rings, because they aren't in the same plane. It's a single molecule. There's no polymerization, I can tell you that. But there is some hydrogen bonding, which does make it look like a polymer. And we'll look at that. And then pi-pi stacking is also interesting. And so sometimes you want to move the molecules that you have such that you can emphasize the pi-pi stacking. But this is a really simple case. Let's just look at this. So to get the dihedral angle, you would want to probably take the nitrogen and the 6 carbons here, and this nitrogen and all these 6 carbons, because those are in a plane, you can see. And it turns out the dihedral angle is 28.1. And how do I? Yeah. I'll tell you later how you get that from the refinement. And then the hydrogen bonding, it's kind of cool. It's called bifurcated because there's 2 donors for 1 acceptor. It's unusual. Put that in to your INS file so you can get geometric information on it. And here's some of that information. For hydrogen bonding, usually you want to see the donor hydrogen acceptor angle is not too far off from linear. It's almost never exactly linear. This one is kind of bent, but I believe it because the distance between the donor and acceptor is still typical for a donor-acceptor distance. And yeah, this is typical too. So anyway, that's the hydrogen bonding. But then to see the real beauty of this, you need the extended structure. And look at the packing. It just goes on and on and on. So that's another, all of these were done with XP, these drawings. And those are 50% thermal ellipsoids, except for the hydrogens, which I usually just draw as simple circles, because those are always isotropic. So another example, using XPrep. You may recognize some of these people too. It was done for Pradeep Mashrak quite a while ago. But anyway, it's a pentadentate ligand, as you can see. And it was deprotonated using sodium hydride and then added to copper chloride. So it was expected to be a copper complex. There was water present because he started with the hydrate. It was in dimethylformamide. That didn't end up in the structure. So XPrep gave this unit cell. This one is monoclinic. You can see because beta is not 90. This was, again, also at 89K. Blue plate, there's the size in millimeters. That isn't in the file, but that was just my notebook. Okay, so XPrep. Yeah. In this case, you see here under the C, there's all zeros. So this is C-centered. It's a C lattice. the original cell was primitive, I think. Well, no, maybe not. Let me see. What's the next page? So, okay. Yeah, if there is a transformation, it will give the transformation matrix. This one, 15, 13, 20, is in the same order, so there was no transformation matrix there. And you can see the matrix is given as 1, 0, 0, 0, 1, 0, 0, 0, 1. That's just a unitary matrix. So the way I input it was the way it ended up, and that's fine. In this case, the e squared minus 1 is closer to centrosymmetric. So even though there are two possibilities, C2 over C and CC, C2 over C is the centrosymmetric one, and that's the one selected because of the e squared minus 1. They both have the same systematic absence things. So this C, H0L, L is odd, would be thrown away. And this CFOM is short for combined figure of merit. So it's taking into account, actually, the systematic absences, the e squared minus 1, plus the frequency with which it's seen. It's taken into account, too, from some old database. OK. Anyway. And unit cell contents. This one is C2 over C. It has 8 general positions. And you look at this and you say, what, 8 general positions? So there's only one listed there. That's a little sneaky, isn't it? So how is that possible? OK, so here's the structure. It has 3 hydrogen bonding interactions, kind of nice. The interesting thing is, thought might be it would be a dimer, and if you change these ethyl groups to propyl groups, it is a dimer. And that was published quite a while ago. Oh, OK. So how do I get 8 general positions? OK, XYZ is always assumed. And then this is the only one listed. And it still signifies 8 general positions. So XYZ and minus XY, a half minus Z. This is due to the C glide. But because it's centrosymmetric, you have to change all 3 signs. So that goes to minus X minus Y minus Z. That goes to X minus Y and a half plus Z. So those are both of the inversions. Then, because it's centered, you have to add a half, 0 to all 4 of those. So you get 4 more positions, general positions, total of 8. But on the sim line, it only looks like 1. But it's really 8, OK? And then, let's go back here. Just wanted to show you. Yeah, we already talked about that. So go in. So, yeah. I worked on a structure that was cubic. FD3 bar C, number 228, had 192 general positions. It's a good thing the program puts them out for you. There were only 95 lines because of the F lattice and so on. OK. So the next few lines, SFAC, unit, tref, HKLF4, and end. OK, we already discussed that. But I wanted to just mention that this SFAC, you can also put it in the long form, and you can mix the short form and the long form if you want to. One advantage to using the long form, it's a little sometimes it's hard to find it, but if you can get it, it has an R in it. So these are all the scattering factor coefficients up through here. But then you have the real and the imaginary part of the structure factor, and mu, the linear absorption correction, and R, the covalent radius, and weight, the atomic weight of that element. Sometimes you want to change R, and this is one way you could change R. Like if you have a copper complex with very long axial bonds, you might want to change R to make sure that that gets connected up. That's one way. There's other ways of doing that. But once you've changed it, then it's going to be fixed for the whole structure. And this is RSIM or RINT, so pretty much the same thing. Again, it's a measure of how well the intensities of equivalent reflections agree. OK. Well, since it's getting kind of late, I'll start this next time. So the student gave me this question. This afternoon we'll talk about this. Just a few years ago, she couldn't figure out what was going wrong, why she couldn't get the structure. It was a borane often they crystallize with this space group that has a threefold axis, because there's three groups around the boron. So she assumed that it was an R3 space group, and that there was this one that was known, published. Couldn't get it though. Okay, so what happened? What did she do wrong? Stay tuned. We'll do it this afternoon. All right? Okay.